Oh, sorry. So what we're going to start with here, guys, is atomic structure, okay, atomic theory, okay, things like that. Hopefully a lot of this will be a review. We're also going to look at history of the atom a bit. You'll find that my notes generally work this way. The first slide is going to have the lesson number and title, and then there'll be some key points there. Okay, the key points are the things you want to really concentrate on as we're going through. When you have your notes package, things you'll want to highlight or make jot notes about, okay, things like that. In terms of note taking, okay, in terms of note taking, that's kind of an individual thing. Did I give you 2 copies of the syllabus? That's kind of an individual thing, the note taking. So whatever works for you, but one thing that you do want to pay attention to is my inflections. Okay, that is, if I exaggerate anything or enunciate anything or really slow down when I'm saying something, okay, or if I underline something on here, that probably means it's important and you probably want to write something down, okay, about that. Lots of times they'll say, you know, this is really something that's, you know, come up on unit exams in the past, or I always put this on a unit exam, or this could be helpful for your lab report. Those are things you want to make little jot notes about. Okay, obviously you don't have to copy everything that's on the board because you're going to have it. Okay, the idea here is you can concentrate more on what I'm saying as opposed to madly writing. Okay. All right, so the key points for today, we want to look at how theories of the structure of the atom were developed. Okay, why did we think the atom looked a certain way? Why did we think then suddenly that that changed? Why do we think it looks a certain way now? Okay, kind of the process through which our idea of the atom evolved. Okay, and secondly, learn the parts of the atom and their characteristics. Hopefully that will be a review. Okay, anybody remember what the atom is made out of? Electrons, neutrons, and one other one. Protons. Okay. Okay. So obviously we remember that. We'll look at how they're arranged and the properties of each one. Okay, stuff like that. All right. So early chemistry was not a science per se. Okay. There were these guys called alchemists. Okay. The aim of the alchemists was to transmute common substances into more valuable substances. Like they would have like chunks of lead sitting around and they would try and turn it into gold, which we know now is physically impossible because of what we know of the structure of the atom. You can't turn an atom of lead into an atom of gold. Okay, it's a fundamental change to the atomic structure of that material, which you cannot do. Okay, of course the alchemists didn't know that. Okay, what they knew was when you mix things together, sometimes it makes something completely different. So they had the idea that if they could mix the right things together, they could change something into something else. Okay? What they didn't understand was the difference between elements and compounds and how a molecule is different from an atom. Okay? And that's what gave them the idea that they could do this. Okay? As an example, sodium is a soft silver-colored metal that, when you put it in water, reacts violently. Okay? Essentially, it explodes. Okay? Chlorine is a green poisonous gas. But when the two react with each other, they create sodium chloride, which we put in large quantities on food. Okay? Two things that would be highly dangerous by themselves can combine and form something with completely different properties. Okay? That was the idea that the alchemists were working on. But again, they didn't understand what the stuff they were dealing with was made out of and how it behaved. Okay? So alchemy was just a trial and error kind of let's see what we can make idea. Okay? And of course, the alchemists didn't communicate with each other. Okay? This was a business. They didn't want somebody else to find out what they had discovered. I mean, if you found the elixir of life, which was another thing that they were looking for, okay, something that you could drink that would make you live forever, okay, well, you probably didn't want to let your formula out of the bag or somebody else would get rich on it. Okay? So they didn't share their findings, which means nothing really progressed. Okay, there wasn't any scientific development because nobody could compare their ideas. All right, everybody follow me there. Now, does that mean the alchemists didn't discover some important things? No. Okay, they discovered a lot about the behavior of matter, okay, and things like that. The problem was that they didn't do it very scientifically. They just went, oh, today I'm going to mix these things together and see what happens. Okay, and then I'm not going to tell anybody. All right, so it just doesn't work very well. Now, obviously we've been using chemistry without really knowing how it worked for a very long time, okay? To do things like tanning leather. Has anyone ever tanned like a animal hide? Okay, it's an interesting process. I did it for the first time this fall, okay? You use a lot of salt and things like that because you want to draw the water out of it, okay? By drawing the water out of it, you hinder the process of decomposition. That is that mold, bacteria, okay, things like that can't grow on it because there's no water. Okay, if you've ever made like jerky, okay, it's a similar process. You throw a whole bunch of salt into the meat to cure it. Okay, again, it draws the water out, it dries it, and it makes it impossible for anything to grow in it. Okay, that means that meat that's not cooked can be preserved without refrigeration for long periods of time. That's all chemistry. Okay, people were using that long before they knew why it worked. Didn't really matter why it worked, it just worked. Okay, and so there was a lot of that as well. Okay, now, development of the atomic theory. We go way back 2,000 years. Okay, the Greeks are kind of, the dominant power in the world. They have a lot of people whose job is to be a thinker. Okay, if you were in ancient Greece, being a thinker was like the best job you could get because basically you sat in the Acropolis and people fanned you with big palm leaves and fed you grapes and you just had to come up with cool ideas. Okay, it was a pretty sweet gig. Right? You never had to get your hands dirty on anything. Democritus was a thinker. So was Aristotle, Plato, those kind of guys. Okay. One of Democritus's ideas was that maybe matter is made up of all these tiny particles, which we know now it's true, but at the time, everybody else went, that's a really dumb idea. We already know what everything's made out of. Everything's made out of 4 things. What were the 4 things everything was made out of? Yeah, the 4 elements: earth, air, fire, and water. Okay? And in fact, the Greeks had a periodic table of sorts to tell you how much of each of those 4 elements something was made out of. Okay? When a volcano erupted and lava came out of it, well, that was some parts fire and some parts earth, because it came out of the earth and it was hot. Okay? Made sense. Right? Steam was some parts water, some parts fire, and some parts air. Okay? Because it went into the air like a gas, like air. Okay? But you needed fire and water to make it. Right? So it all they had this really logical system for figuring out what things were made out of. Okay? Mercury, for example, was some parts earth and some parts water because it was a metal, but it was a liquid. Okay? So things like that. But it made a lot of sense. It was actually a fairly scientific way of cataloging the materials that they dealt with regularly. Unfortunately, of course, it wasn't right. Okay? So anyway, Democritus was told, yeah, you know what, forget about that idea. It's not right. Think up something else. Well, it wasn't all bad for Democritus. He did think up something else. Democracy. Yeah, not a bad thing to think up. Okay, so it wasn't all bad for Democritus. But his idea died essentially for about 2,000 years. Okay, before a scientist was doing some experiments and realized that, you know what, there's this idea of tiny particles actually kind of explains what I'm doing. Okay. Now, we've already talked about the alchemists a little bit here. Okay, they were kind of the next step in that. That's what an alchemist's lab might have looked like. Preserved alligator hanging from the ceiling for some reason. Okay, all kinds of balances and burners and flasks and beakers and grinders and all kinds of stuff. Okay, would have been a typical lab. Okay, for an alchemist, I think that's Leonardo da Vinci's lab. Okay, but that's kind of, they would have had all that kind of equipment around. What turned alchemy into chemistry and took it into being a respectable science was these 2 guys. Okay, Roger Bacon and Antoine Lavoisier. They developed the scientific method. Okay? Before that, chemistry was alchemy. It was trial and error. Mix these things together. If nothing happens, try something else. Okay? These guys said, we never learn anything that way because we're never testing things properly. What we need is a method that controls certain things in an experiment and eliminates other factors from our experiment. So we know the effect of one thing on another. Okay? So in other words, you need to have a problem that you're investigating, and only one problem. Only investigate one thing at a time. Okay? And when you choose that problem, you should already have an idea of what's causing it. Okay? In other words, you should have a hypothesis. Okay? Then you need to come up with a controlled experiment or a procedure to test it. Okay? And this procedure should eliminate all factors other than the ones that you're experimenting on. Okay? When that experiment is done, you should make accurate recordings of your findings, and then you should compare them with your hypothesis. In other words, you should do analysis. Okay? Your analysis should lead you to whether or not your hypothesis was right. In other words, a conclusion. Okay? They had developed the scientific method and took alchemy forward, okay, and turned it into chemistry, and made it a respectable science. Okay? That was kind of their very important contribution. Okay, the idea of the atom. Okay, you can see here at the bottom of the text that I have a sentence that is bold-faced and italicized. It's important. It's basically the definition of an atom. Okay, what's an atom? An atom is the smallest particle of an element that still retains the properties of that material. Okay, so the example here is if I had a chunk of lead and I had a really sharp cutting apparatus that I could keep cutting this chunk smaller and smaller and smaller and smaller. All those small pieces, no matter how small I cut them, would still be lead. They would still have the same properties, the same density, okay? The same ability to conduct electricity, okay? The same reactivity with other things. They would all be the same. They would all have the same characteristics. Okay? If I could keep cutting smaller and smaller and smaller, eventually I would get to the point where I couldn't cut it anymore. And what would I have? I would have a single atom. Okay? That's actually what the word atom means. It comes from the Greek word atomos, which means uncuttable. Okay? You can't take an atom any further. Now, can we split an atom? Yes, we can. Not with a knife. Okay, that's a good thing because otherwise you could split the atom while chopping carrots at home. Okay, you don't want a mushroom cloud forming in the kitchen. Okay, we can't obviously split the atom that way. Okay, it requires a lot of specialized equipment. But if I can get it down to that level, I can't cut that any smaller. If I do manage to split that atom, it's no longer lead. It's now two atoms that are different. Okay. And they would have a different number of protons, a different number of electrons, different number of neutrons. It would be a different material. Okay? So for example, if I took, let's say, an atom of oxygen, okay, which has 8 protons, it has 8 neutrons and 8 electrons, and I cut it in half. Okay? Not that I could do that, but if I did, it would no longer be oxygen, because I'd now have 2 atoms that had 4 protons. Essentially, I'd have something else. Now, it doesn't work that way. Okay, I'm kind of giving you a fake situation here, but I'm doing it to illustrate that when you take apart an atom, you change what you have. It's no longer that material anymore. Okay, for an atom to be oxygen, it's got to have 8 protons. It's got to have 8 electrons. It's got to have 8 neutrons. Otherwise, it's something else. Okay, and as soon as I take something away from it, I change what it is. All right, everybody follow me there? Okay, that's what the alchemists didn't understand. Okay, they didn't understand that to change lead into gold would require them to change the very structure of the material they were dealing with. And you can't do that. Okay, it doesn't matter what I mix together. I'm not changing the atoms that I have. I might make them go together, so they're not separate atoms, they're now a molecule, and that's going to have different properties. But that molecule still has the same atoms that I started with. I didn't change the elements themselves. I changed how the atoms were arranged, but I didn't change the atoms themselves. Okay, that's the key thing. Okay. So, 1700s. John Dalton is doing experiments with chemical reactions. And what he's finding is that when he reacts two things together, his products have different physical and chemical properties, but they're still made of the same materials that he started with. Okay? Which leads him to believe there's something about those materials that can't be changed. And that leads him back to what Democritus said, which was the smallest unit of matter is an atom, and that atom can't change. Okay? That's what started Dalton's atomic theory. Okay? Was noticing patterns in the chemical reactions he was dealing with. Okay? So the example I gave you earlier was if I mix sodium, which is a explosive silverish metal, okay, with chlorine, which is a green poisonous gas. If I put them together and they react, I get sodium chloride, which is table salt. Okay, but I still have sodium atoms and chlorine atoms. They're just stuck together now. Okay? I still have the same materials as before. All right? So Dalton's atomic theory had 4 points. Do you suppose that could set up easily for a multiple choice question? Like, which of the following is not part of Dalton's atomic theory, and have 3 out of the 4 of these there? Okay? That would be an easy thing for me to do on, let's say, a unit exam. Yes, write that down. Okay? Because I'm going to do that later. Okay? So the first point of the atomic theory, all elements are composed of tiny, indivisible particles called atoms. For all intents and purposes, we know that to be true. We can split the atom now, but it's not something that happens typically naturally. Okay? Some things break down because they're really, really big, okay? But they don't generally split radically. Okay? Second point, atoms of the same element are identical. So if I had a whole bunch of oxygen atoms that I could actually see, I wouldn't be able to tell them apart because every single one of them would be the same. They'd all have 8 protons, okay? They'd all have 8 electrons. Maybe a few of them might have different numbers of neutrons. We'll talk about that another time, okay? But they're all identical, okay? That's what makes one element different from another. What do the atoms look like, okay? Hydrogen atoms are really simple and really small. They have 1 proton and 1 electron, okay? Right up here, the smallest and simplest of all the atoms. Okay, if I go down over here, okay, I start dealing with atoms that are really, really big on the periodic table. Okay, so an atom of hydrogen has 1 proton, 1 neutron. Okay, and an atom of now, however you say it, it's one of these new ones that they discovered. Okay, has 112 protons, and it has 165 neutrons, okay, and it has 112 electrons. That atom is considerably different than an atom of hydrogen, which is why they have very different properties. Okay? Now, in general, the bigger an atom gets, the less stable it is. Okay? That's why hydrogen is the most common element in the universe, and those other ones are only created in a lab. Okay? Specifically, the lab would be things like the Large Hadron Collider, okay, and things like that, where they smash atoms into each other and try and make bigger ones. Okay, so those atoms typically don't exist in nature, and when they are created, they don't last very long. They break down really, really fast. Okay, they're radioactive and they break down. Right? Typically, large atoms. Okay, you can see on the periodic table there, a lot of those ones that are large are things that we know are radioactive. Some of them are things that we use in nuclear power plants, like uranium, plutonium, okay, things like that. All right, now, how does a nuclear power plant work? Does anyone know how that works? How do we harness the power of the atom in a nuclear power plant? Well, if we allow them to decay naturally, we get a little bit of energy, but the process is really slow. We want it to go faster. So instead of letting them decay naturally, which they would do, we break them. We split them. We shoot things at them, okay? Like other smaller particles, like neutrons and things like that. We shoot them at these big atoms and make the atoms break. Well, when they break, they release lots of energy. Now, I'm not talking that you'd ever notice one atom of uranium splitting, because you wouldn't, okay? But when you have a whole bunch of them together and you get them all to break around the same time, it releases a lot of energy. Okay? Now, if that's uncontrolled, you have a bomb. You don't want that. Okay? In a nuclear reactor, you want to control how much of that energy happens. So, I'm going to show you how to make a nuclear bomb in a nuclear power plant. Not that you'd ever be able to make one, but okay? It's a lot more complex than what I'm going to show you. Okay? In a nuclear reactor, you have essentially an emitter that shoots small particles at fuel rods. Fuel rods are just metal rods, okay? And on these rods are pellets made of uranium, usually, okay? When the particles come out of there and they hit these uranium pellets, the uranium atoms get broken, okay? And when they break, their pieces go off and they break other atoms, okay? And they release the energy. Now, this all happens underwater. Okay, or at least near water, so that we can use the heat that's generated by this to boil the water. When it turns into steam, it can turn a turbine, and that generates electricity. Okay? That's how you make electricity with a nuclear power plant. Okay, to make a nuclear bomb, you want the process to be uncontrolled. Okay, we can control this process by exposing more or less of the fuel rod to the emitted particles. Okay, if we lift it back out, then the reaction slows down. If we put more of it in, the reaction speeds up. Okay? In a nuclear bomb, you take a big ball, essentially, of the fuel, okay, plutonium or uranium or whatever, and you enclose it in high explosive, okay, like C4, plastic, okay, something like that, right? And what you do then is you blow up the high explosive, but you shape it in such a way that all the debris from the explosion shoots inwards at the big pile of uranium, okay, which essentially acts the same way this does. Okay? Those particles start splitting uranium atoms, which break, and they break other uranium atoms, and it's a chain reaction that leads to kaboom. Okay? Now, it's a pretty simple idea. Getting your hands on the necessary materials is the difficult part, luckily, because there are obviously crazy people out there who would want to build one. Yeah? Okay, yeah. It's really hard to get your hands on concentrated uranium for some reason. Okay? All right, so that's essentially how they work. They are breaking atoms and then releasing the energy that was previously holding those atoms together. Right? What's the problem with this? Well, the waste products of this are not only energy, but also highly radioactive toxic waste. Okay? And you have to put that somewhere. Unless it's a bomb, then it just destroys everything. Okay? Okay, point number 3. Atoms of different elements can combine with one another in simple whole number ratios to form compounds. Probably the most important part of that is this. Atoms combine in whole numbers. That is, you never have a compound that has half of an atom in it. Because if you have half of an atom, you've split an atom and you no longer have that stuff, you have something else. Okay? So, when we look at something like water, well, water is written like that. For every oxygen, there are 2 hydrogens. Nobody writes it like this. Right? Yeah, there's half as much oxygen as there is hydrogen in a water molecule, but you never write it like that because that implies there's 1 hydrogen atom and half an oxygen atom, which you can't have. Okay? They always go together in whole number ratios. Okay? So you might have something like this. Sodium chloride, 1 to 1. This is 2 to 1. Okay? 3 to 1, 4 to 1, 4 to 3, whatever it happens to be, but they're always going to be whole numbers because you can't have parts of atoms in a compound. Okay? Everybody all right with that? Right? That was one of the things that led Dalton to developing this atomic theory. Was all of his reactions showed that all the material he started with was present after the reaction as well. Okay? All of it. All right, the 4th thing was the death blow for alchemy. Okay? Once Dalton understood that number 3 happened, number 4 was intuitive. Okay? Chemical reactions occur when atoms are separated. So if I took sodium chloride and I broke it apart, I would have sodium and chlorine. I'd have 2 separate elements. So that, molecules can be broken apart. The atoms can't be, but the molecules can be, okay, in a chemical reaction. Okay? They can be joined. I can put them together and make a molecule. Okay? Or rearranged. I can take 2 molecules and react them with each other, and they'll switch. They'll switch around. We'll talk about that more when we talk about chemical reactions. But okay, those are the things that happen in a chemical reaction. I don't actually turn one element into another. Okay? That's what Dalton discovered. If I take sodium and chlorine, I make sodium chloride. I still have sodium and chlorine. I didn't magically make lead. Okay? I didn't change the starting materials that I had. I changed how they were arranged, but I didn't create anything new. Okay? That's what alchemy was trying to do. Okay? And this sort of proved that can't happen. Okay? Questions there? All right. So definitely know those points. 3 and 4 are the ones that typically come up on an exam in terms of explanation. Okay? Like I might ask you, explain why the alchemists could never, do what they wanted to do, transmute lead into gold, using what you know of atomic structure. Well, that would be talking about 3 and 4 in your own words, okay? Showing me that I can apply what I learned, yeah? Okay, that kind of stuff comes up fairly often. All right, As soon as Dalton came up with that theory and people liked it, okay, the points made sense, he had scientific evidence of it, the next natural question was, okay, what's an atom look like? Dalton didn't really have a good answer for that. Okay, we didn't know about protons, neutrons, and electrons, so he didn't know that atoms were made of 3 parts. Okay, so he said, I don't know, you can't cut them, they're really small. I guess they're probably like a sphere, because what, spheres occur in nature, right? Planets are spheres, stars are spheres. It kind of made sense. That's a naturally occurring shape. Okay, let's go with that. They're just a ball. Okay. Well, there wasn't anyone to say otherwise, and it kind of made sense. I mean, it wouldn't have made sense to say they all are cubes, okay? Because cubes don't occur in nature, okay? So that didn't make much sense. So the sphere was kind of a natural choice, okay? And that people were fine with that for like 130 years or so, okay? Until Dalton's model was the solid sphere model. Okay? That was fine up until a guy named J.J. Thomson started doing experiments with what's called electrochemistry. Okay? Essentially, he was working with the stuff that would become wet cell batteries. Okay, like what you would have in your car that's used to start your car. And that's a wet cell or lead acid battery. Okay? He was working with those kinds of chemical reactions. He was finding when I put these things together, I make electricity. Well, Dalton's atomic model of a solid sphere didn't explain where the electricity came from. Okay? He knew a chemical reaction was going on. He knew what his end products were, but he couldn't explain where the electricity came from. So he said, something's wrong with Dalton's model. It's lacking something. So here's what I'm going to say. I know there's charges that can move in a reaction, so I'm going to say that the atom has 2 parts. It's still a sphere, but the sphere is positively charged. And embedded on its surface, because positive and negative attract each other, are these little tiny particles that have practically no mass that are negative. Now, why he didn't call them negatrons, I'll never understand, but he called them electrons, I guess, because they make electricity. I don't know. Okay, but they're negatively charged particles. They're embedded on the surface. Okay, so he kind of kept part of Dalton's model, but improved on it a little bit to help explain his findings. Okay, so we went from solid sphere, and J.J. Thomson discovered electrons, and came up with the plum pudding model of the atom. After this, things really get crazy. Okay, if there's small negative particles, why aren't there small positive particles? Okay, and if there's small positive particles, where's all the mass? Okay, these were kind of questions that started coming up when people started doing more and more kind of significant experiments and things like that. I mean, this is the turn of the 20th century. Okay, so it's more than 100 years ago now. Okay, but shortly after this is when guys like Oppenheimer and the guys who developed the atomic bomb started working on nuclear physics, okay? And they needed to know the structure of the atom to make that stuff work, okay? That's when they started discovering these other particles like protons and neutrons and started coming up with ideas of what does the atom really look like more accurately, okay? So shortly after that, okay, protons were discovered, okay? Obviously it's a positively charged particle, not a big solid mass that's positive, but small particles that are positive, okay? The key thing here, the number of protons and the number of electrons have to be equal, okay? Because an atom doesn't have a charge, okay? That means the amount of positives and the amount of negatives have to be the same. Right? They knew that kind of from the get-go. So they said, all right, these are the 2 particles that make up an atom. Shortly after that, people said, if there's only 2 particles, matter is really heavy for some reason. And these 2 particles can't account for all the mass. So there's got to be something else in there. So the natural idea was, okay, there's 1 more particle in there. And it's neutral because we can't have another charge. There's only positive and negative. So that was kind of the idea of neutrons. Okay? Neutrons essentially help to make up the extra mass that people couldn't account for. Okay? So Chadwick is the guy who came up with the idea, okay, of the neutron. Okay? Once the 3 particles were decided on, then it was a matter of what does it look like? Okay? Are they all bundled together in the middle? Okay? Is it like planets orbiting the sun? What's going on in there? How do we know what these things look like? Okay? there were all kinds of models out there. There were modifications of the plum pudding model that had them all embedded in this solid mass. Okay, there were some that were like this, where electrons were all the same distance from the nucleus. Okay, things like that. None of them were really could explain everything. Okay, it wasn't until a guy named Ernest Rutherford came along and ran an experiment that was really quite simple. Okay, that proved the nuclear model of the atom, proved that atoms have a nucleus. That's where the protons and neutrons are, and that electrons are in this area around that. Okay? An atom, realistically, is mostly empty space. That was the problem with solid sphere and plum pudding. Okay? They imagined that the atom was this ball. Okay? But then that meant that there wasn't a lot of empty space around. Okay? We realize now that matter is actually a lot of empty space. So Rutherford's experiment involved a lot of older technology that you guys probably aren't even familiar with. Back in the day, cameras had stuff in them called film. I don't know if any of you have ever even seen a camera that actually has film. Okay, you guys are like the total digital generation now. Okay, photographic film works this way. If you expose it to light, it changes color. Right? So when photons, which are light particles, essentially hit it, okay, those spots where they strike are exposed and they get brighter. Right? And that's how photographic film worked. Okay? So what Rutherford did is he set up an experiment where he had a source of particles, almost like an X-ray machine, okay, and he had a piece of thin gold foil. So imagine like tin foil, but made out of gold. You certainly wouldn't wrap your potatoes and throw them on the barbecue with that. Okay? He had gold foil for whatever reason. Okay? And he shot these particles at it. Now, his idea was that there's so much empty space and the nucleus is so small that all these beams will just go right through the gold foil and there'll be this big exposed area on the photographic film behind. Okay? He figured that atoms were that small. Okay? What he discovered is that actually a lot of the particles got deflected. Okay? Proving that there was a central dense nucleus, which we'll talk more about tomorrow. Okay, make sure you get the notes package in whatever form you feel you're going to want it. Okay, have that ready for Thursday at the latest.